Okay, this is Giancoli chapter 23, problem 12, and the problem reads that a dentist wants a small mirror that, when 2 centimeters from a tooth, will produce a 4 times bigger upright image. What kind of mirror must be used, and what must its radius of curvature be? So, this may be the first mirror diagram and mirror equation problem that you've done. So let's think about this, and this may not be obvious until you've done several of these problems. But the answer is going to turn out that this needs to be a concave mirror. Oops. Need concave. And to prove that to you, let me instead, show you, let me first say that a flat mirror doesn't do any magnifying whatsoever. An image looks as large as the object. But let me convince you that a convex mirror will always give you a smaller image. So let's do this. Let's consider what a convex mirror does. And whenever you're doing these kinds of drawings, what you want to do is always indicate your optical axis, which I'll do here. That's just the axis of symmetry for that mirror. Let me try this one more time. Good enough. And I will draw the general shape of this thing. So it's going to have some slight curvature to it. And it's bowing outward with nothing going on behind it. The shiny surface, the reflective surface, is here. Now remember, this is considered to be a spherical mirror. That is to say that it represents a piece of a surface of some sphere that has a particular radius. So the center might be somewhere, let's say, over here. And the focal point would be considered to be here. Again, it's not like any light rays can get back there, but that focal length on some level it's half the distance of the radius of curvature. In fact, let me go ahead and write that down. The focal length is equal to the radius of curvature, r over 2. And now I think what I actually want to do is just maybe make this absolute value, because remember, for a convex mirror, the focal length is defined to be negative. Really, that's because all the things that appear back here, these are considered to have negative distances. That's just how we get the equations to work out right. And everything out in front, if you like, in real life, has a so-called positive distance. And that will matter when we go to use our equations. But at least for now, let's use the diagram, which is very good for getting a qualitative sense of what should happen. You could put the object anywhere. And again, I'm showing you what's going on for a convex lens to convince you that you're never going to get an image enhancement. In other words, you're not going to get a magnification bigger than 1. So, you could put an object, let's say over here, represented by this arrow. And if you ask, what do the beams do, the rays of light that, scatter from this object, the most special ones that we want to consider are the ones that come in perfectly parallel to the horizontal, that is to say they're parallel to the optical axis. And what they do is they reflect away from the focal point. So that means I should draw that ray does something like this, because that would be moving away from this. And in fact, I'm going to extend this line to prove to you that not only does it move away from F, and it goes off in this direction, but also if anyone else was out here looking at these rays, they would say, hey, there's a ray that comes from back there, or at least it looks like it. That is considered the so-called virtual ray, or that is considered a virtual ray. You can play the same game with other rays. For example, this thing should work going backward, so any ray heading toward the focus should end up bending perfectly, parallel to that optical axis. So that's the other one I can draw. The other ray I can draw from here, headed straight toward the focus, the focal point. But when it gets there, that's not terrible. Let me try this one more time. When it gets there, bink, good enough. It should reflect parallel to that axis. So that is to say, this incoming ray was headed toward the focus, but then got deflected away. And again, anyone that's back here that's going to see that ray coming toward them, they're going to say, hey, it looks like it came from back here. And once you get those two rays, in this case, two virtual rays, to intersect, you conclude that that is where the image appears to be. So again, for vocab, this is considered the object. This is considered the image. The image is upright, but is most certainly smaller. That is to say that the magnification, which is given by the height of the image divided by the height of the object, which, as it turns out, is also equal to minus the distance to the image over the distance to the object. In this particular case, this is certainly going to be less than 1. And it actually doesn't matter how close you bring the object to the mirror. You can actually make the following statement that a convex mirror always has a magnification, well, let's see, less than or equal to 1. There's a special case in which the magnification would be equal to 1, but it's never going to be bigger. So if you buy that, then let's carry on and draw the correct diagram with a concave mirror, because apparently that's the only thing that has the possibility of working. Okay, and I'm going to just kind of draw the mirror looking sort of like this. I want to draw it thin because that makes the geometry work out nicely. So this mirror has a radius of curvature, and the center of that circle, I don't know, I'm going to have to estimate. It could be something like this, C, and then that would mean that the focus is halfway from that point, to the mirror. Okay, good. So we've got that. And let me convince you of a couple things, and you might have already seen this in those previous examples I did, but if your object is, let's say, far away like this, then you could ask, where does the image show up? And you can start drawing your rays. I always like to start with the one that goes parallel to the optical axis. Okay, the ray comes in, and by construction, this thing is made to reflect through the focus. Okay, good. That's ray number 1. And you could pick many other rays. You could have a ray go through the center, and the special thing about the center is that rays that go through the center get reflected directly back through the center. So let's try to do that through the center. Dink. Let's try that one more time. Dink. And well, I'm just going to draw right over it. It sort of does that. Okay, that's that. And once you get an intersection of two rays, then you're already going to make a prediction for where the image should show up, and that would mean it should be here and it should be upside down. And what you're going to notice is that this image is well, let's see, it's inverted or upside down. It's certainly smaller, and I would say it's real as opposed to virtual. Again, it is formed by the intersection of actual light rays. It is not merely apparent, not apparent by the intersection of virtual rays. If you find this unconvincing or are worried about, if you've done this right, then you can always draw 1/3 ray, and that ray would be, rather than having a horizontal ray which bounces through the focus, you could have a ray go through the focus, and that ray, dink. Oh, it didn't make it straight. Anyway, suppose that was straight. That ray should get reflected parallel to the axis. It's sort of doing what the red line did in reverse. And if you draw this carefully enough, you'll find good enough consistency that all 3 rays intersect there. Okay, but notice you end up with a smaller image, and it's inverted, which is not what you wanted, not what the dentist wants. The dentist wants something that's bigger and right side up. And so what that means is that we have to experiment with where this thing should go. So let me, I suppose, copy and paste. And I'm going to sort of leave, I'm going to end up changing a lot of this. So let's get rid of these rays. What I want to do is move the, I want to move the object and convince you of what's going to happen when you move it close enough. There's something special that happens. When you move it closer than the focal length, that's when you get special behavior to occur. Can I convince you that this is true now that I've erased some things? Again, the center, I was sort of guessing that it was going to be 2.5 earthing. I don't know. So suppose this is the center, and that means this is the focal point. Okay, if you put your object close enough, and by that I mean if you put it past the focal point, what happens? Well, let's see. And in fact, I encourage you to pause the video and try to do this on your own so you really get your hands dirty and start to get an appreciation for this. I will start with the horizontal ray. That one we know is supposed to get reflected. Come on. Toward the focus. Okay. Well, a ray that goes toward the focus, you might think that's supposed to get reflected. Well, I can't send a ray directly toward the focus from the object. It would not hit the mirror. On the other hand, a ray that goes toward the mirror as if it passed through the focus already, which is like what this would do, come on, would get reflected going horizontally. I noticed that I have not done this, not color-coded this. My apologies. This thing goes up and reflects that way. This thing goes over and reflects this way. And remember, 2 rays are enough to figure out what's going on. This ray that got reflected toward the focus would appear as if it came from back here. Again, that is the virtual ray. Likewise, the other one would appear to have come from this direction. Finally, we conclude, therefore, that the image must be here, and you'll notice that it is upright and larger. Image is upright, larger, and you'll notice that it is in fact virtual because it's not really back there, but it is apparently there, and we can determine that by the intersection of virtual rays. Okay, hopefully you're convinced now that it takes a concave lens to do this, and we have drawn the relevant diagram. So what remains to do is to simply use the equations we have at hand. Magnification is equal to height of image over height of object, but that's also equal to the distance to the image divided by the distance to the object with a minus sign in front. That is the magnification equation. The mirror equation relates the focal length to the distance to the object and the distance to the image. And lastly, remember that the focal length is given by a half of the radius of curvature, which means that well, if you wanted to solve for the radius of curvature, which we do need to do that would mean the radius of curvature is twice the focal length. In this problem, what they actually are telling us is that the magnification is 4, or 4.0. What you're also told is that the tooth being 2 centimeters away, that means the distance to the object is 2 centimeters, and by definition, the object distance is always positive, but just to verify, it is in front of the mirror. And that allows us to start making some progress. So let me call this equation 1, and this equation 2, and this equation 3. So we're going to use equation 1 to show that the magnification 4 is equal to, we have no information about the size of the object, its image height or object height. So let's instead use that second equality and relate the distance to the image minus the distance to the image divided by the distance to the object, which is 2.0 centimeters. And so from this we can conclude that the distance to the image is equal to minus 8.0 centimeters. Okay, it's a negative number, which confirms to us our suspicion that the image should end up behind the mirror, and therefore it's virtual. That's consistent with what we've drawn here, although admittedly I drew this pretty crappily. It's not clear that the image is 4 times the distance that the object is from the mirror surface, but anyway, that at least seems plausible. So let's use the second equation to solve for the focal length, which we will apparently need to get the radius of curvature, which is what we're after. 1 over the focal length is apparently equal to 1 over the distance to the object, 1 over 2.0 centimeters, plus 1 over the distance to the image, minus 8.0 centimeters. We need to solve for f, so let's combine these fractions, finding a common denominator. 1/2 is the same thing as 4 over 8 centimeters, minus 1 over 8 centimeters, which is, of course, 3 over 8 centimeters. You conclude then that the focal length, is 8/3 of a centimeter, or 2.667. And then, finally, using the third equation, r is equal to 2f, and that is 16 over 3, or approximately 5.3 centimeters. So the radius of curvature for this mirror is 5.3 centimeters, and it must be concave for reasons that we have just explained.